I'll just give you a thumbs up in a moment.
Okay. So hello, everyone. Welcome to the Topos Colloquium today, 19th of May. It's a great pleasure to have Alexandra. Well, you guys sometimes say Alexandra, but I say Alexandra because she's Portuguese and we speak the same language. And so Alexandra Silva is a professor in Cornell University, and she moved there recently. So she has lots of work still with people in University College London. And kind of she has lovely things on her website. You guys should go and check the projects and the papers and the talks. And I'm supposed to say something, Alexandra, about why kind of I think it's such a good thing to have you coming and talking to us. And I think this is because, you know, your work on algebra is really a landmark in the work in category theory and computer science, both in specification, verification, and all this stuff. So it's a real great pleasure to have you with us. And Alexandra is going to then, can you start sharing your slides again?
Yes, I will.
Because otherwise I'm going to mangle your title. So Alexandra is going to talk to us about learning weighted automata. Take it away, Alexandra.
Okay, thanks, thanks Valeria for the kind introduction. And yeah, I indeed did a lot of my work on algebra. And what I will show you today, I will hide a little bit those details, but I'm happy to answer questions on it. And a lot of the results I'll show you today actually were designed and were derived from a categorical framework that I developed in the last few years together with a student who's now a postdoc called Herco van Heert, who worked for, during his graduate work time, he worked on understanding algorithms, active learning algorithms from a categorical perspective and how to use category theory to actually develop new algorithms for new models of automata. And so today I want to tell you about this algorithm we developed for weighted automata, which was really rooted in a categorical framework, even though I will only share a little bit of that along the way. So I know that you guys are probably mostly interested in the sort of ins and outs of the category theory and the proofs, but I thought it would be nice to start this talk by actually telling you a little bit about the motivation for these active learning algorithms and how they are used, and then some of my more practical work that I've been using this on. So this area of active automata learning, the sort of key idea behind it is that you assume you have a system, and by a system you can think, you know, a piece of software, a piece of hardware. This is a very abstract sort of view, but so you have a system and you can interact with the system in a well-defined way, but you cannot look at the source code. So you can do what is called a black box or closed box interaction. So there's some interaction alphabet and you can sort of ping the system in some ways and the system reacts and you can observe the reactions. And through these black box interactions, the goal of active learning algorithms is to incrementally build models of what might be running in the system. And as you incrementally build this model, you might have, you might have some ideas of what is running and you have some properties that you can model check, and you might get some counterexamples and you use that, and it's sort of an iterative process and you refine your model. So in the slide here on the right side, I actually have a model that was automatically inferred from an implementation of TCP/IP inside Windows 8. And this was done fully automatically, and it was they knew they were learning a TCP implementation, but they didn't look at the code, and so this was what was inferred. And for those who are familiar a little bit with TCP/IP, if you look at this model, you will recognize some of the sequences from the handshake and how things were inferred. And the nice thing about this learning algorithms, these active automata learning algorithms, is that the whole process is very much automated, meaning there's something happened here. Can you see my screen? my screen suddenly went blank. So the whole process is automated, and there's very little human intervention needed, which is nice. Sort of in terms of, you know, actual algorithms, the work in this area goes back to the 80s and goes back to the work of Eric Gold and then Dana Angluin. And they developed algorithms for a very, very simple class of black boxes, if you like. So they thought of these black boxes as having inside a regular language, or if you want, having some behavior inside that can be described as a regular language. So maybe the whole behavior is not a regular language, but there's parts of it that could be captured as a regular language. And so Angluin in 87 introduced this algorithm where if your black box is a regular language, you can interact with it through two ways. One is to ask this, what is called a membership query. So you can ask your black box, is a certain word accepted? And the black box will give you as an answer yes or no. And you start recording your answers inside a data structure called an observation table. And you gather this information as you go along. And then at some point, you have enough information in this table that you think, I can make a guess. And I'm going to guess that your language is a certain automaton. So there's this one-to-one correspondence between certain tables and automata. And then the black box, and this is one of the assumptions in Angluin's algorithm, the black box has this magic capability of telling you if you're right or not. And I'm using the word magic here because really this is a very strong assumption. So you assume that your black box not only can interact with you, but at some point can also tell you if you're correct or not. And this is sort of what is called a perfect oracle situation. So you're trying to infer the behavior that this perfect oracle is holding. And you assume that as a perfect oracle, the oracle will know when you're correct or not. As you can imagine, in real life, perfect oracles don't exist, and this is a very strong assumption. But for the theoretical properties of the algorithm, it's sort of a nice setup. And then I will reflect a little bit how we can actually implement such oracles in practical terms. But imagining that we are in this perfect oracle situation, so you give the oracle your hypothesis, and then the oracle will say yes if you're correct, or it will say no and give you a counterexample. And what's going to happen is that by using this counterexample, you're going to refine your knowledge of what's happening in the language. And in Angluin's algorithm, what this iteration does is that it learns the minimal automaton. And so this is a crucial point of the algorithm, because regular languages have unique representatives as minimal deterministic automata. The algorithm pretty much approximates that minimal automaton by making sure that through every equivalence query, and every time you're doing an equivalence query, either you've hit the number of states of the minimal automaton, or through a counterexample, you discover a new state, meaning that after a finite number of steps, you're going to really hit that minimal automaton. And this is sort of how you prove correctness of this algorithm, and how you then can use it. Now, as I said, this original algorithm of Angluin and also the other work by Gold, they all had very strong assumptions. So one, they assume your black box is running a regular language. Two, they assume that you have a perfect oracle. This does not happen in practice. However, LSTAR has actually made its way to mainstream verification, and it has by now been used to do quite cool analysis work in practical implementations. So one I sort of already showed you a glimpse of is this work on learning models of TCP implementations. And so there's this paper from about 7 years ago on combining model learning or automata learning and model checking to find bugs in TCP implementations. You can do other things with it. You can learn how certain implementations, certain libraries, how you can actually reach errors inside certain libraries. So this is another work that used LSTAR to learn sequences of function calls that always lead to errors. And LSTAR has been applied also to learn the protocols that run inside chips of certain bank cards. So on the slide here, I have an example of a Visa debit card, but it's been applied to other cards. It's also been applied to learn models of the chips that are inside your passport. It has been used to learn models of other network protocols, SSH, QUIC, and it has been used in very, very different sort of application domains. The common thing being in those application domains, like in TCP/IP and QUIC, in this sort of network protocol world, or in this world of protocols running inside a bank chip, a bank card chip, or a passport chip, these are all behaviors that clearly can be described as a finite state machine. In fact, if you look through the RFC of a lot of network protocols that is described in English, it comes very often with a finite state machine sort of highlighting how things really are supposed to work. And so this is sort of where LSTAR and these methods have found a really good application domain. It's parts of programs and protocols whose behaviors that you're really interested in can be described as a finite state machine. And in particular, as a finite state machine that accepts a regular language. So very simple sort of deterministic finite automata.
Alexandra,
Now,
one question, sorry, just a minute. Do you want questions in the middle or at the end?
Anytime. I'm happy to take questions in between. Whenever people want to interrupt, feel free. It's fine.
So I have a question already then, because
okay.
I'm a bit surprised about, I mean, having a perfect oracle would mean just saying yes or no, right? This one is more than perfect. It produces a counterexample. Where does this counterexample come from?
Yeah, so the assumption here is that the oracle is holding on to the actual automaton. And that when you give it your hypothesis, which is a different automaton, it will sort of play an equivalence game to find where the two automata differ. Now, this is if the oracle indeed has an automaton. Now, in practice, the oracle does not have an automaton. So how does this work? So in practice, what you do is you have a hypothesis, which is an automaton. The system is some code, some description. And what you do some sort of fuzzing, some fuzzy testing, or some bounded model checking where you say, you know what, I actually don't mind if the systems are not exactly the same, but I care about traces of length 100. And so then there are ways of checking that up to that length of trace, you have the same thing. And if you find a counterexample up to that length, you just refine your model and do it again. Okay, so the LSTAR algorithm I showed you a few slides ago, and I will go into detail in a second, was done for deterministic finite automata. And nowadays, I mean, the models we use in verification, but also in semantics, very often have quantities. So one example is a weighted automaton, which is basically an automaton that every action comes with a weight from a semi-ring. Maybe it's a resource cost, maybe it is a distance between nodes. There's many interpretations you can give to these weights. But in essence, imagine a deterministic finite automaton where you added some cost everywhere. And so it is a natural question to wonder if you can move the learning algorithm from learning regular languages, which are subsets of words, to weighted languages, which are objects that are not so different. I mean, you move from having a function into the Boolean semi-ring to having a function into an arbitrary semi-ring. And so what can we do if we have an arbitrary semi-ring? Can we just run the same ideas? And where are the challenges in these extensions? So this is what I basically want to tell you about today, is starting from LSTAR, which is a well-established active learning algorithm for deterministic finite automaton for regular languages, with the same assumptions as LSTAR. So the oracle can answer membership queries and equivalence queries. What do I have to do to actually be able to learn a weighted automaton? So let's go through exactly how LSTAR works, and let's actually run an example so that you see what really happens through the membership queries. So we have these membership queries and these equivalence queries. Those are the two types of queries we're going to have. And if there's no in the equivalence query, I'm going to get a counterexample. Now let's run the algorithm. So the algorithm is here on the slide. It only has 3 steps, really. So we're going to build an observation table, and this observation table is going to record the outcomes of membership queries, and it's also going to be used to also store the counterexamples. And so how is this going to work? We're going to start from imagining that our automaton, so the language we're trying to learn, is the simplest language possible. It has one state. That's it. There's only one state. And if there's only one state, then the table will only have information for one state. And so basically that's how the algorithm starts. It starts by initiating the table to imagining that it only has one row, and that row is labeled by the empty word, which I denote here on the slide by epsilon. And then the algorithm is going to start asking membership queries. And by doing so, it's going to close the table. And I will explain in a second what that means. And at some point, it will have asked enough queries that it thinks it can make a conjecture. So it can ask an equivalence query. And it asks an equivalence query. And if the teacher says no, so if the oracle says no, it will take the suffixes of that counterexample and it will add it to the columns of the table. So I'll explain why we change the rows and the columns in different times. So let's look at this example. Let's imagine that the teacher, so I refer to the oracle sometimes as the teacher, that's terminology Angloan used. So the teacher or the oracle are holding on to a language that is the language of words over a singleton alphabet that has numbers. The number of A's is divisible by 3. So it's a simple language. This is what the oracle is hiding. And now I'm the learner, so I'm trying to learn what the oracle has. So I'm going to run the process from Angloan. So I'm going to start with a table, and I'm just going to first write the empty word on both the rows and the columns. And I'm going to ask the oracle, what happens for the empty word? And the oracle is going to tell me the empty word is accepted because it has 0 A's, and that's divisible by 3. So I put a 1 there, and I'm writing the 1 in red. And so at that point, as I said in the beginning, I'm conjecturing. I only need one state. So I have that one state. I know it's accepting because I asked the oracle. But now I need to write the transitions. So I need to know what happens after 1A. And when I check what happens after 1A, so I ask the oracle, what about A? The oracle actually says A gets rejected. And because the oracle tells me that A is rejected, I actually know one state is not enough. Because if I have a word that is accepted and a word that is rejected, then my language has at least 2 equivalence classes. So I need 2 states. Okay, so I update my knowledge. I say, okay, I know I need 2 states. So, okay, I'm going to need 2 states, one accepting, one rejecting. How about now? Can I make an equivalence query? So I check again, what happens after 1 more A? And the oracle says, oh, 2 A's are rejected. And I say, aha, I know what the language is this automaton in the slide with 2 states, one accepting, one rejecting, and then it loops in the last state because after 2 A's, I'm in the same place. So at that point, I can ask the oracle, what do you think of my conjecture? And the oracle says, oh, that's nice, but you misclassified the word with 3 A's because the word with 3 A's is now rejected in my automaton, but it should be accepted. So I take that counterexample and I say, okay, this counterexample tells me that my state with accepting and rejecting words, the fact that I know there are 2 states, there's something here that I should split further. So there's an equivalence class of words that I misclassified. So how do I do that? So I add the counterexample to the columns of the table. What will that do? That will give me more information about each equivalence class. And so the row for epsilon, which is one state, is the accepting state, now has also information about whether the word AA, and AAA is a member of that equivalence class. And you can see in that first row in red that I know that epsilon and AAA, the word with 3 A's, belong to the same equivalence class. I also know that A and 2 A's do not belong to that equivalence class, and are in fact, they are not in the same equivalence class themselves, because if I look at the blue and green row, I now see that they are different. So at this point, I know that I made a mistake before, and I actually need 3 states. And so I add my third state to the table, and I ask what happens after one more A. I always need to ask in this process what happens in the next step so that I know if I have enough states. And at that point, I indeed can draw an automaton with 3 states, a red state, a blue state, and a green state. And this is basically counting modulo 3. So the accepting state counts modulo 0. The first state knows that I still need to count 2 more A's. And the third state knows I still need to count 1 more A. And now with 3 states, I'm done. So I can ask the oracle, and the oracle will say, yes, you're done. And this is what happened in this process I showed you, what we're doing, really. We're finding the different equivalence classes in your regular language. So there's this result that tells us that the minimal automaton accepting a regular language is the states are what are called Myhill narrowed equivalence classes. And what this data structure, this observation table is doing is really storing in each row an equivalence class. And that's why there's this one-to-one correspondence between rows and states in the automata. And so this is how we discovered this minimal automata. And so the algorithm terminates because at every loop iteration, I added 1 new state. I don't know if you noticed that, but every time I went through 1 loop, I actually added 1 more state. So at some point, we know this language is accepted by a minimal automaton with 3 states. And therefore, once I hit 3, I know I found my automaton. So that's how termination goes. And this algorithm is correct by construction. So it terminates with a minimal automaton for that language, because we are assuming that the oracle tells us we are correct. So if the oracle is saying you're correct, then we're correct. And so correctness and termination go hand in hand here. Okay, so now this is LSTAR for the deterministic automata. And so now what is the difference? Like, what are the things that change when you move to weighted automata? So the first thing that changes is that in weighted finite automata, the states are not anymore final or non-final. They output a number. They output a number from your semi-ring. In addition, for every letter, for deterministic automata, I make 1 transition for every letter. For weighted automata, I now make not 1 transition, but I make a transition to a vector of next states. And so I really, given a semi-ring, what I'm really doing when I transition, I'm transitioning to an element of the free semi-module over my state space. So if my semi-ring is a field, then what I have is a linear map between states for the transitions. So I'm really making a transition between a state and a linear combination of next states. If I have the Boolean semi-ring, then I have non-deterministic automata. So I'm transitioning between a state, and for each letter, I have multiple states possible in that transition, or 0, and so on. So for every semi-ring, you can sort of imagine what the free semi-module is, and then interpret transitions. But abstractly is like a function from states. I go with a letter to an element of this free semi-module. And the weighted automata accept weighted languages, which are functions from A star to the semi-ring. And the way these functions get computed, they use the semi-ring structure. So you might have in each automaton, in each weighted automaton, multiple paths labeled with the same word. And so you compute for each path a weight by multiplying, by using the multiplication of the semi-ring along the way. And then you add up the weight of your multiple paths. And that gives you the weight of that word. So let me show you an example. So here's an example with two states over, let's say, the natural numbers. So every transition has a letter A, and is labeled with a weight, in this case 1, 1, 2. And the initial state here outputs 0, so the number 0, and the other state outputs the number 1. So what does this automaton recognize? So if you do a little bit of calculations, you will see that, well, the empty word is in the state that outputs 0, so that's 0. After I read 1A from the initial state, I can either stay in that state, and that's going to cost me 1 times 0, or I can make a transition to the next state, and that's going to cost me 1 times 1. And you can continue doing this with 2A's and 3A's and so on, and you will see that it assigns to the empty word 0, to 1A to 1, to 2A's 3, to 3A's 7, and if you stare at it for a little while, you will actually see that for every word of length n, it will assign the number 2n minus 1. Okay, so that's sort of the function that this automaton is computing. And most of the times you can sort of see what function is computing, not always, but with simple semi-rings, this is usually possible. So when we are learning, so if we want to adapt a learning algorithm, there are some things that immediately stand out, right? So you know that the membership queries will now have to return me some value in the semi-ring, because my function does not assign accept or reject anymore, but it assigns a value. So whenever I ask the Oracle, what does this word do? The Oracle has to tell me 5, 7, 10, it has to tell me a weight. That recording those membership queries, I will have to, in the table, so in the observation table, I will have to write these numbers as well. So the table will be the same, except that the entries, the cells, will have values from the semi-ring rather than 0, 1. The membership queries will have to return a weight associated with the word. And the equivalence queries will have to basically tell me a counterexample, a word that is misclassified. Now here I should say, it is known that for certain semi-rings, equivalence is undecidable. So there's this semi-ring called the tropical semi-ring, which basically uses as multiplication max. And it is a semi-ring that is very useful to compute shortest paths, but it is the equivalence of weighted automata over that semi-ring is undecidable. So here you start seeing that, this assumption that the Oracle can do equivalence is also much trickier here, because it won't work for every semi-ring. If the semi-ring, if weighted automata, if you can decide equivalence over that semi-ring, then you can make the assumption. So fields is known, the natural numbers is known, Noetherian semi-rings is known. So there's a bunch of known results on this, and so we can use that. But for the purpose of presenting the algorithm, you can even go as far as ignore that and say, oh, I just assume my Oracle somehow magically can solve an undecidable problem and tell me an answer. And that's also fine in terms of the setup, but one has to be conscious that this assumption is now even stronger than before. So how does it look in terms of the actual algorithm? And this is sort of where things are when category theory really helped, and I'm not showing you that part, but the fact that, let me go back just for a second. I mean, when you look at these two arrows, it's in fact, the move from DFA to WFA is really just a move in the base category in some ways. So for deterministic finite automata, these are functions over sets. For weighted automata, in fact, you have the same functor almost, but over 3 semi-modules. And so what you're doing in terms of the learning, you're almost combining 2 learning processes. One that learns the structure, which is a transition structure, in a different category. And then you have to sort of figure out the algebraic structure of your state space, which is now these free semi-modules. So let me give you a very concrete sort of instance of this. If the weighted automaton is over a field, then in essence, what your learning algorithm is trying to do is two tasks. One is to find the dimension of the field, the dimension of the vector space you're working over. So the language that the oracle is hiding has the structure of a vector space, and every vector space is free. So you know that there will be a basis for that vector space. So one task that the algorithm has to do is figure out what is the dimension of my vector space. The second task is, what is the transition structure in the automaton? And so these two tasks, in the case of deterministic automata, are collapsed into one task because the algebraic structure on the state space was just a set. But now the algebraic structure on the state space is, for instance, that of a vector space. So you are not only finding the transition structure of your automaton, but you are also discovering this algebraic structure in your state space. And where does that pop up? That pops up in building the table. So let me show you how the table is now built. So when you are closing the table, when you are building the table, before we were just checking if a row was new, because that meant I have a new state. Now we are not going to check if the row is new. We're going to check if the row is a linear combination of other rows. Because by doing that, we are in essence checking whether the vector space I'm trying to build, if it's a field, if we already have enough elements for the basis. If we do, then every new row I see will be a linear combination of the other rows. If I see a new row that is not a linear combination, then I know that in fact I need more dimension in my algebraic structure. And this starts, adding certain constraints on which semi-rings I can use, because in order for me to be able to check that a row is a linear combination of other rows, I have to be able to solve linear systems of equations, which for fields, again, we know it's possible and we can do it. But how about for other semi-rings? Can I do it? So let me show you a concrete example of how the algorithm runs. So let's run this algorithm again, but now remember that my entries in my table will be natural numbers. Or integers, let's say integers. So I have the oracle. The oracle is holding this language, 2 to the n minus 1. And so I ask the oracle again, what do I do with 0? The oracle says, what do I do with the empty word? The oracle says 0. What do I do with a? The oracle says 1. 1 is not a linear combination of 0 because I cannot obtain 1 by multiplying a scalar by 0. So I know I have two vectors, a vector space of dimension 2. And then I ask, how about 2a's? And then I get a 3. And at that point, 3 is a linear combination of 1. I just multiply by the scalar 3. So again, I pass on my hypothesis. I say, oh, I think I have two states. One makes a transition from 0 to 1. And the other one loops with a scalar of 3. And the automaton says, no, that's wrong. You did not classify well A. Again, the same counterexample. So we extend the table again. We write down the numbers that the oracle gives us, and these are the numbers it gives us, 137 and 13715. And then we ask, how about AA? And we get 3, 7, 15, 31. And now if you stare at this row, you will see that you can obtain this row from the other two by doing 3 times the row for A minus 2 times the row for epsilon. So if you check, for instance, the fourth column, 3 times 15 is 45, minus 14, that's 31. And you can check that indeed this row for AA is not a new row. It's 3 times the second one minus 2 times the first one. And so you again ask the oracle, how about this one? Do you like this one? And and the oracle, at this point might say yes, and you're happy. Now, this example is a very, I crafted this example to show you. So you might wonder, did it terminate by luck? So was I able to draw this automaton by luck? And also note that the automaton I learned is quite different than the one the oracle was holding. They both have two states, so that's great, but the transition structures are different. So the first automaton had an extra transition in the initial state, whereas this one has all the transitions in the second state. And you can check that they produce the same function. But definitely you start seeing a problem here, which is for the same number of states, I have different ways of building the same function. So this uniqueness of minimal representatives is not there anymore. And if you take the Boolean semi-ring, which gives you non-deterministic automata, this is a classic result that there are no unique minimal non-deterministic automata for a language. So at this point, you might wonder, does the algorithm terminate? How can I know if the algorithm terminates? And for DFAs, the termination very much depended on this uniqueness of minimal deterministic automata. So what happens now for weighted automata? Well, it will depend on the semi-ring. So for a field, if the automaton is over the real numbers, we know that every vector space has a basis, and this basically gives us termination. So what you need to prove in the algorithm is that you're indeed making progress towards the basis. And the algorithm I just showed you will instantiate, in the case of fields, to an algorithm that existed before. In the case of the Boolean semi-rings, weighted automata are non-deterministic automata, and the algorithm recovers a result by Bernard Bollig and collaborators from 2009. And what it is learning a subclass of non-deterministic finite automata for which minimal representatives exist. For other semi-rings, you need to be a bit more careful. And yeah, the bottom line is, the answer is no, it does not terminate for every semi-ring, because there will be semi-rings for which we cannot guarantee that the approximation is working. So the question is, how do we characterize the semi-rings for which it works? I mean, I showed you two examples. It works for fields, it works for the Boolean semi-ring, and these were results discovered completely independently and focusing on that structure. And what I want to argue is that, in fact, it's more general than that. And this termination property is really a property of the semi-ring, and we can obtain it just by looking at what the semi-ring allows you to do in terms of the algorithm. So let me just make a comment on this example I gave you, because I was a bit sneaky. I said that I was learning over the integers, I think I said at some point, and you could even say you're learning over the rationals. And this was the example I gave you. And I said, oh yeah, now the third row is 3 times the second one minus 2 the first one. And I was a bit sneaky because, in fact, this example is really where the problem, illustrates where the problem is. So if I did not have access to negative numbers, so if I was, say, over the natural numbers, look at the automaton on the top of the slide, which is the automaton the oracle is holding. The oracle is holding an automaton only with positive numbers. So the oracle could tell me, no, you have to learn over the natural numbers. I am not giving you an answer if you give me negative numbers. And in this case, even though I discovered 2 states, I am not able to discover the right weights. So in fact, this only terminates, this example, which is a simple example, only terminates if I say that I'm learning over the rationals or the integers or the real numbers. Because without that -2 there, I don't have a way to update my knowledge about the first state and finding that loop around the first state. If you look carefully at that automaton over the natural numbers, you will notice that the first state has output 0. So in fact, every trace that stays in that loop is given weight 0. And that weight 0 is actually functioning as a minus. So whenever, let's say I look at a trace of length 3, there will be several ways of building this trace of length 3, including going through this state in which I give output 0, meaning I'm deleting some of the options of learning a trace of state 3. Whereas in the second automaton, so the automaton that the learner was able to find, that deletion is explicit. It says, whatever you do with traces of length 2 or higher, you always need to do -2 times that last A. So in fact, if I run the process like I did before, over the natural numbers, so if I keep asking the Oracle membership queries without having the -2 or any negative numbers, this just keeps going. So the rows just keep expanding and expanding and expanding. And in fact, the process never terminates. You can check that every single row I'm discovering cannot be written as a linear combination of the previous rows if you are only allowed to use positive numbers. So in fact, the row for AA is again 3 times the row for A -2 times the row for epsilon. So the linear combination is still there. It's just that now I cannot use it because I'm only allowed to use positive scalars. And so this is the problem, is really how do I solve systems of equations over a specific semi-ring? And in essence, what the algorithm is doing is there's this infinite matrix that has the whole language. And what the algorithm is doing is trying to find a finite fragment of this matrix that is enough to represent the language. And this matrix, when you fix the natural numbers, it's not finitely generated because the semi-modules over the natural numbers are commutative monoids. And as it turns out, for this language, for the language 2 to the n-1, this matrix is not finitely generated. It is, however, finitely generated over the rationals or over the reals or over the integers. So it is this question, if I am able to write this infinite matrix, can I decide if it is finitely generated over my semi-ring of interest? And sometimes it is, and sometimes it isn't. And how can we find that out without having to look at this infinite object is really what the algorithm is trying to do. So here are the termination conditions that we came up with, and they are general over semi-rings. So the algorithm needs to come equipped with a progress measure. So in the case of deterministic finite automata, this progress measure was really just finding new states, a new row, a new row. So every iteration of the loop, I had a new row. Now that's not enough because now there's this added complication that we're talking about a space spanned by multiple rows. And so what we came up with is that we have this progress measure, and I will instantiate it for specific things. And it's basically a number that we guarantee will always increase when you process a counterexample. Okay, so that's sort of the key point. Then on top of that, we need to know that the language that we're trying to learn, which is represented in this infinite matrix called the Hankel matrix, we need to know that that language, the language we're trying to learn, satisfies the following condition. Whenever I take sub-semi-module chains, meaning if I increase the number of rows and I look at the space that those rows span, that chain is a chain of sub-semi-modules, and you get an increasing sort of chain that converges. And it at some point, you converge, and from then onwards, you cannot find new things. What is this sort of trying to generalize? So imagine for vector spaces, okay? You're increasing the dimension of your space. At some point, you will hit the dimension of the language. And what this condition says is, okay, when you've hit the dimension of your language, if your language is a vector space of size 3, if you know you're on a basis of size 3, you will never need a basis of size 5 to represent that, because you have your basis. And you might draw the transitions in an isomorphic way, but the size remains constant. And so this ascending chain condition for sub-semi-modules is really just generalizing the idea that for vector spaces, I can refine the size of my bases through these iterations. And so if we assume these two things, then the way you prove termination of the algorithm for all semi-rings, or for the semi-rings that satisfy this, you basically say, okay, I'm going to start with my table. I'm building my table, and I am going to basically be building a chain of modules that are approximating the Hankel matrix. And the Hankel matrix is really the language the oracle is holding. And that chain will converge. And when it converges, I really do not need to find new rows. I mean, at that point, my table will be closed. And that's it. It's closed. I can make a conjecture. Now, that conjecture might be wrong. I might have only seen like a little bit of my language. If that conjecture is wrong, the oracle will give me a counterexample. And then I use my second condition. I say, oh, when I get my counterexample, I'm going to refine my columns in my table. And that tells me that I've increased my progress measure, tells me that I've increased my dimension. And so I run again the closeness procedure. And I know I'm making progress towards my language. And basically what this progress measure tells me is that there will only be finitely many counterexamples, because at some point, since I'm making progress in every iteration, I will have hit the size of my space, whether it's a field or a commutative monoid or whatever semi-module I'm looking at. There's a notion of dimension, and I'm going to hit it. Okay, so these are sort of two abstract conditions. So let's just see what they instantiate to. Let me just show for a field. So for a field, this progress measure is simply the dimension of the vector space. So it's the size of your bases. And we know that the size of the bases is smaller or equal, or is equal to the size of the minimal weighted automata. The ascending chain condition just says that the minimal weighted automaton will have the exact same dimension as the Hankel matrix. And every time we run the loop in the algorithm, we're going to be increasing the dimension of your vector space. So at some point, I'm going to hit the one I'm looking for. And linear systems, to check for closeness, is just Gaussian elimination. We've all learned and know how to solve this. If the semi-ring is finite, then you can also define a progress measure, which is just the set size of the semi-module. And you can say that the Hankel matrix dimension will always be smaller than the determinization of the automata. And again, you can solve systems, because since the semi-ring is finite, you can just exhaustively enumerate all linear combinations, and then you check if any works. How about fields and finite semi-rings? These are all okay, but can we do more than this? So can we do anything about, the integers or anything else? So what we showed in our work is that actually you can go as far as what is called a principal ideal domain. And many of you probably know what this is, but so a principal ideal domain is an integral domain with all ideals being principal. What does this mean? An integral domain is a commutative ring that has the property that, if you multiply A and B and is 0, then one of them has to be 0. And the fact that all ideals are principal, they say that this is generated by one element. So what are examples of these principal ideal domains that might be interesting? We have the integers. So one of the examples I showed you, the problematic example, was over the integers. We have polynomials over a field. We have Z modulo I, and there's a bunch of interesting sort of examples that are not fields, that are not finite semi-rings, but are principal ideal domains. And for principal ideal domains, there's a lot of work on what a module is and when is the module free. And this is sort of standard. A module is free if it is torsion free, meaning that you can only multiply, if you multiply by 0, if the multiplication yields 0, then one of the elements is 0. And the sub-module of a free and finitely generated module will be free and finitely generated and will have a smaller rank. So now here you see, right? PIDs, so principal ideal domains, are really faking fields because they give you these properties that you need, which is there's a notion of rank. So think of rank as the dimension of the basis for fields or for vector spaces. And there's this notion that if you take sub-semi modules, you're still, or finitely generated ones, you're still finitely generated. And that's exactly what we need for the algorithm. We need that when you have these finitely generated free modules, that you can sort of make progress and find more and more equivalence classes. And so PIDs are sort of have the minimum amount of requirements to allow you to do that. And that's, once you discover that, and this was part of the sort of the challenge was how to discover these conditions. But once you discover this class of semi-rings that actually have these conditions, then the proof is not itself so hard. And so you can basically learn over PIDs by defining this progress measure as the rank of the module spanned by the table, which we know because this is a PID that is free and finitely generated. And then the ascending chain condition is there. I mean, so this requires a proof, but you can prove that they satisfy this ascending chain condition. And then it turns out that, because these are nicely studied algebraic structures, that someone already studied how to solve linear systems over these. And there's something called the Smith normal form, and there's some assumptions on computability that you have to make to solve equations, but these hold for the integers and for other PIDs, and you can then check for closeness. So actually the learning algorithm just instantiates completely, once you have the general proof that has those abstract conditions, you can instantiate it to anything for which you can make these conditions concrete. And even though I did not show you the category theory that's behind some of these arguments, there is category theory hidden in there. And it's really coming from this general categorical view on learning. So this terminates for the integers, and that's nice. And it sort of was what we were looking for. So the sort of key takeaway I hope I gave you in the talk is that ultimately, these algorithms that are there and were designed for deterministic finite automata, they can really be extended to other automata if you stop for a second and reflect on how actually automata are all viewed as arrows in a different category. And you really just need to understand the algebraic structure of the category to be able to generalize these algorithms. And in the case of weighted finite automata, the termination of the algorithm has nothing to do with the automata. It's really about the semi-ring. It's all about the semi-ring. It's all about the algebraic structure that underlies the languages. And this is, to me, this is fascinating because when you think about algorithms for automata, it is often the case that you think that they very much depend on the transition structure. And what this shows is that actually the algebraic structure of the state space is equally or even more important for a lot of the algorithms. And this is really for the learning part, this was the crucial observation. And moreover, once you move into this world of quantitative automata and weighted automata and probabilistic automata as well, you really, if you're trying to find the equivalence classes of languages, you need to know how to solve finite systems of equations, because ultimately what you really want is to have a finite representation of your language. And that finite representation comes with an automaton or a finite system that has finite number of states, even though it spans a large, once you construct the vector space, it's an infinite state space, but it has a finite basis. And it is the finite basis you're looking for. You don't want, computer scientists like discrete structures. We are not so comfortable with continuous stuff. And therefore, you're always looking for ways to go back to your finite representations. And in order to do that, in the case of learning, you really need to be able to solve this system of equations. And you need to be comfortable with going out there and finding methods to solve these systems of equations for different semi-rings, for different structures. And this is very much, I hope the message that I managed to pass on. So I'm happy to take questions now. I know I'm running a bit late, but I think we have a few minutes for questions if people want to ask about the theory part. I'm also happy to tell you a little bit more about the practical side of learning. So thank you.
Thank you. Thank you so much, Alexandra. That was fantastic. Very, very interesting indeed. Thanks a lot. And I think we do have a few minutes for questions, and we normally do the following. We have a few questions, and then we stop the recording and kind of carry on a little bit more if you can have some 10 minutes extra. But this was really good. Give me a hand, Toby, if I'm not seeing hands up from people. Can you see?
So far there aren't any, but I mean,
Andreas wants to say, but unmute yourself, Andrea.
Okay. So let's see. I have 2 questions. One about the PID in the later part of the talk. It seems to me that a lot of what you were saying, like submodules of finitely generated modules are finitely generated, is in fact true for broader classes of rings. I guess that's true for arbitrary Noetherian rings. So what happens, for instance, if I take a polynomial ring in 2 variables over a field? That's not a PID. That's a very nice Noetherian ring. What happens with the termination of the algorithm?
Yeah, that is a good question. So let me say 2 things. So first, for equivalence of weighted automata, indeed, Noetherian semi-rings is sort of the limit where people go, and it is a natural question why we didn't go to Noetherian here, because indeed, since the equivalence works for Noetherian, why didn't we go? So we have 2 conditions, right? One is the progress bound, and the other one is this ascending chain. Mm-hmm. And for the ascending chain, that is very close to the property of being Noetherian. But for the progress bound, you really need to be able to measure the size. And for that, we use this notion of rank that PIDs have. And for arbitrary Noetherian ones, we didn't know how to do it. So this is the problem. And this does not say, and I should have said that, this does not say that PIDs is the largest class for which we can do this. It's the largest class we know how to do it as of now. There might be, other subclasses of Noetherian rings for which we can say something, but as of now, this is how far we went.
Very good. Could I ask another question? Much earlier in the talk, you mentioned rather briefly that for some semi-rings, it's undecidable whether 2 given weighted automata are equivalent. Is there a characterization of which semi-rings are the good ones and which are the bad ones? Or is it just try each one separately and hope for the best?
So no, so unfortunately, so here's what we know. The proof of undecidability for the tropical one is a 100-page paper that Daniel Kropp wrote in the 90s, and it's a whole it's a single project. It was about that semi-ring. Then people tried very hard to get classes for which it is decidable. So Zoltan Eshek and collaborators, and then me and Stefan Milius and some other people proved independently using two different ways that for Noetherian semirings, it is decidable. So that's the largest class that we know. Plus, Zoltan, using a very different technique, proved it for the natural numbers. And that's, again, a sort of standalone proof. It does not generalize to much more. And then there's also more recent work by Stefan Milius, where there's a class he calls proper semirings that includes all Noetherian, the natural numbers. I'm not sure it includes any new ones, I now forgot, but he did a categorical proof. And that sort of encompasses some of the previous proofs we had. So that's sort of the largest class I think we know right now. Do we know more than the tropical for undecidable? Not really. It's very difficult to prove that equivalence is undecidable. And the proof of Krob is really a tour de force. I mean, it's really amazing.
Okay, thank you.
I think Toby had his hand up and I didn't see it. So go ahead, Toby.
Yeah, I do. I didn't know when we were supposed to stop doing the live streaming, but if it's okay, I can ask my question. So earlier in the talk, you mentioned, I mean, occasionally in the talk, you mentioned kind of the role of category theory, and you talked about how it was helpful in improving, or in getting kind of grips on the structures, or maybe even help improve some of these, say, termination results. And you indicated that there was this, you were thinking about kind of something like a base change from the kinds of semi-rings or the semi-modules. And I was just wondering if you could sort of indicate what kind of tools, or how the kind of category theory was helpful, at least whether it was helpful for the kind of termination proof, or whether, yeah, I'd just be interested in hearing a little bit about it.
Yeah, so, let me preface my answer by saying we all know there's no free lunch, right? So ultimately, at some point in your proof, you need to get your hands dirty. So if if you want to conclude something about a certain semi-ring, if Krob took 100 pages to prove undecidability, it's not like out of a sudden now we're going to magically, in one page prove that. The point, and I think this is something that that is really beautiful in my, my personal opinion, is how you can isolate where you need to get your hands dirty. So in our view of learning, we think of automata as arrows in a base category. We don't need to make any assumptions to begin with about the base category. We just need to know that the category has products so that we can have a function for outputs and a function for transitions. We need exponentials. If you have a finite alphabet, you can get away just with products. And you say, okay, what is an automaton? Okay, an automaton is an arrow that takes states to an output plus some transitions. Once you have that view and you have said nothing about the base category so far, you can start talking about what is the language of an automaton. Well, if you're lucky enough, your category is nice that that functor of output times to the A has a final call algebra. Yeah. And you just say, okay, maybe in my nice category, that's even like functions from A star to O. And you show that that's your final call algebra and say, okay, that's my final call algebra. Yeah. And now you can start talking about things like minimal representatives. You say, well, if my category has epimonofactorizations, then I'm going to say my minimal automaton is just, I look at my arrow into the final call algebra, I factorize it, whatever image I get there, I don't know what it is, but I know it exists and it's the minimal one. And then you say, okay, now I have this minimal thing and I want to approximate it. And so you just start playing, you just make things concrete when you need them. And you need that very, very later, very late in the algorithm. And so the things that get really concrete, and that's when your hands, when you need to go and look at concrete papers, are things like, how do I know I've discovered a new state? How do I do reachability in my category? That is not something you can just sort of take out of your category theory hat. You need to then get down to the concrete algebraic structure. But up to the point where you need to do that, you can phrase everything very abstractly, and you can even sketch the termination argument under the abstract assumptions. It's just later on that you need to make things concrete. And so you isolate the places where you need to reach out to, to your commutative monoid references or any other sort of structure you're looking at.
Okay, thanks. I mean, yeah, that was interesting. I guess I was expecting maybe something along the lines, I guess maybe you're pointing at it, of kind of the functor you're talking about, of which you've got co-algebras kind of factorizing into this kind of transition part and then this algebraic part. And I guess you did mention that kind of these two parts of the thing that you've got to learn.
Yeah, so the category we end up working on is an Eilenberg-Moore category.
Yes.
And so then that's where the two things sort of appear, right? You have your Eilenberg-Moore category and you have a structure there, and then you have your transitions and you have a final calls for your functor. And so that's where the generality was in our work.
Okay, thanks.
So maybe we should kind of thanks Alexandra and carry on a little bit longer, unless you prefer to have forever and ever in YouTube my question, which is about the applications. What sort of?
Yeah, I'm happy for you to stop if you want, and then we can continue informally. That's fine.
Sounds good. Sounds good. Then can you do it, Toby?
I can. Yeah.
Thank you very much again.
Thank you. I'll stop sharing my